Calculation of density of unit cell. So here we have the formula for density of unit cell, D equal to Z capital M divided by A cube N. So here D is density of the unit cell which we want to calculate. Z is the number of atoms present in unit cell. Now for each different types of unit cell, whether it is simple cubic cell, BCC type of cell or FCC type of cell, the Z is different for each cell, and that we have already seen how to determine. M is the molar mass of the element and A is edge length of the cube and Na is Avogadro number constant. Okay, so how to calculate this density using this formula and how we have achieved this formula, that we will see. So here mass of the unit cell, if we consider, that will be equal to number of atoms in unit cell, which is Z, and mass of each atom, which is small m. Okay, so mass of each small atom, that is m, and total number of atoms in the unit cell is Z. So if we multiply this, we will get mass of the unit cell. Okay, now mass of an atom present in the unit cell, that is m. How to find out that? If capital M is the molar mass, then we know that in 1 mole there is how many number of atoms? Avogadro number. Now Avogadro number Na is 6.023 into 10 to the power 23. So this number of atoms present in 1 mole. Okay, so this number of atoms will have mass of 1 mole. So molar mass is m. So this number of atoms will have mass capital M. Fine. So one atom will have mass m by this number, or we can say m by Na. Okay. So for each small m, the value is m by Na. So in place of this equation, we can write Z into m by Na. Okay, so this is mass of an atom present in the unit cell, that is m by Na, and when we are multiplying Z with it, that will give us the mass of the unit cell. So if the Z value, suppose for BCC it is 2, then we will write 2 into m by Na. For FCC it is 4, so 4 into m by Na. Okay, now density is mass by volume, and mass we have already calculated, which is Zm divided by Na. Okay, and what is volume of the cube? The volume of the cube is simply A cube, because A is the edge length of the cube. Okay, so in place of volume we will write 1 by A cube. So finally the equation becomes Zm Na A cube. So this is equal to density. So this formula, in this way we can derive this formula, which is already mentioned here. Now here we have one constant, this value of Avogadro constant, that is known, and Zm A cube and D. So among these 4 values, if one of the values is unknown and rest of the 3 values are known, we can easily find out the unknown value. So suppose in some case D value, Z value, A3, all these are given, that is edge length is given. So in that case, by putting all these values, we can find out the molar mass. Similarly, if Zm A value is given, we can find out the density. Okay, so this is the importance of this formula. Now we will apply this formula and we will see how we can find out one unknown value. So here, which unknown value we have to find out? Let's see. A metal occurs as BCC and it has a density which is given, that is D value is given 7.856 gram per centimeter cube. We have to find atomic radius of the metal. Okay, so atomic radius of the metal, suppose it is R. Atomic mass is given. Atomic mass of the metal that is given, which is 58 gram per mole. Fine. So atomic radius of the metal for BCC lattice. Now first of all we will write the formula that we have just derived. Zm AQ Na, and then we will put the known values. So which values are known here? Density is given, which is known. Molar mass is given or atomic mass is given. Okay, and Na value we already know, and as it is mentioned that BCC type of lattice, so Z value will be 2, that is also known. So here only unknown element is A. So we will write AQ Z M D Na. Now we will put all the values. 2 into 58 divided by 7.856 multiplied by Avogadro number 6.023 10 to the power 23. So after calculation this will be equal to 2.45 into 10 to the power minus 23, because 10 to the power 23 it is in the denominator. Now we will arrange the value in this way, 24.5 into 10 to the power minus 24. So why we have done so? Because when we will take cube root, then minus 24, if we keep it in this form it will help us. Okay, because cube root of 10 to the power minus 24 it will be 10 to the power minus 8. So directly that is the calculation will become easy. So the value of A will be 2.9 multiplied by 10 to the power minus 8, and the unit of this edge length will be centimeter, because be very careful about the units. You have to put the values with the same unit. Suppose here it is mentioned in gram per meter cube or per decimeter cube. So in that case the length, edge length value that we will get, that will be in meter or decimeter. So we have to be careful about the units. So here A is 2.9 into 10 to the power minus 8 centimeter. Now centimeter, normally as this value is very small, what we do, we convert it to picometer. Now 1 picometer is equal to 10 to the power minus 8 centimeter. 1 picometer 10 to the power minus 8 centimeter. So that is why this will be equal to, sorry, it is minus 10, not 8. 10 to the power minus 10 centimeter. Okay, so next what we will do, we will again arrange it in this way. 290 multiplied by 10 to the power minus 10 centimeter. So now it will be equal to 290 picometer. But this is not the radius, this is simply the edge length. Okay, so A is edge length, but we have to find radius. But we know for BCC what is the relationship between A and R. By applying that formula we can find out the atomic radius R. So R is basically equal to, for BCC type of lattice, R is equal to root 3A divided by 4. And if you cannot remember this formula, you can easily simply draw the BCC lattice like this. And in BCC lattice there is body center, and this is the corner, this is another corner. So this length, which is the body diagonal, that is root 3A, and that is equal to 4R. So by drawing that formula also you can calculate this formula. So now we will put all the values, that is root 3 into 290 divided by 4, and this will be equal to 125 0.57 picometer. So this is the value of radius. Okay, so this is the atomic radius. Another problem we will solve. Copper crystallizes in FCC structure. If two neighboring atoms are at a distance 234 picometer, then we have to find out the edge length and also the volume of the unit cell. So here, first of all, we have to draw the FCC cubic cell, okay? Because in FCC structure, the nearest atoms in FCC crystal structure are along the phase diagonals. In case of BCC, it is along the body diagonal. But in case of FCC, it is along the phase diagonal of the cube. And they are in contact with each other. So this is the phase diagonal. If you join the line, this is the phase diagonal. Okay. And if the edge length is A, then the value of this phase diagonal will be root 2a. Okay. Now here this 234 picometer, this value is given. It is actually nearest distance. That means if we consider center of one atom and center of another atom, which is very touching each other, so this distance is actually 234. So this is the nearest distance, 234 picometer. But we have to also remember that this from center up to the circumference, this distance is r and this is also r. So basically 234 is actually equal to 2r. Okay. So what we can write? We can write that 2r equal to 234, where r is atomic radius. So if 2r equal to 234, we can find out the value of r, which is 117 picometer. Fine. Now we have to find out edge length. That is, we have to find out A, edge length of the cube. So for that, what we'll do? For FCC, the relationship between r and A is r equal to A divided by 2 root 2. Okay. So if this is the relationship, this relationship you can also reach. If you can remember this formula, it is fine. But if you can't remember this, just remember that this body, if this length is 234, it is actually 2r. This distance is 2r. So the whole length, that is the whole phase diagonal, it will be 4r. That means root 2a, that is equal to 4r. So from that we can reach this relationship. So A will be equal to 2 root 2 multiplied by r. That means 117 2 root 2, and that is equal to 331 picometer. So this is the edge length. Okay. Now what we will do? We can convert it to meter, because it is not mentioned in the question that whether you have to express the volume or edge length in any particular unit. So you can keep it in this unit, that is picometer, directly you can keep it. But if options are given, that is in options if units are mentioned, or even there is no option and simply written that find edge length in meter or centimeter, then accordingly you have to convert it. So if it is picometer, if we want to convert it to meter, it is simply 331 multiplied by 10 to the power minus 12 meter, because 1 picometer equal to 10 to the power minus 12 meter. Okay. So in this way we can find the edge length in terms of picometer unit or in terms of meter unit. Next we will find out what is the volume of the unit cell. Now when we know the edge length, it is very easy to calculate the volume, and the volume will be A cube. So A cube is, you can also write it as 3.31 into 10 to the power minus 10. So 3.31 10 to the power minus 10 cube meter cube. So this will be equal to okay. So 3.31 into 10 to the power minus 10 whole cube. If we take this, if we do the calculation, it will be 36.26 into 10 to the power minus 30 meter cube. Be very careful about the units. Imperfection or defects in crystal. So crystals, we know that there is regular arrangement in the whole crystal, but that does not mean that there is no defect. If we consider a very large portion of the crystal, there may be some defect. So ideally perfect crystal is one which has the same unit cell and contains the same lattice points throughout the crystal. That is, in the whole structure there will be the same arrangement. But if there is deviation from this ideally perfect crystal structure, then we will say that there is presence of defects. So this term imperfection or defect, when we use, when there is deviation from ideally perfect crystal from the periodic arrangement of its constituent, and these are very common. Okay, so there are different types of defects. Here we have a flow chart. So from this flow chart we can see that crystal defects broadly can be classified to line defect and point defect. Now line defect we will not go into detail because that is not in syllabus, but only point defect we will focus mainly. Now under point defect there is stoichiometric defect number 1, impurity defect and non-stoichiometric defect. Okay, now under stoichiometric defect we have total 4 types: Schottky, Frenkel, interstitial, vacancy. And under non-stoichiometric defect there is 2 types: metal excess, metal deficiency. Again under metal excess defect there is 2 types: presence of anionic vacancies, presence of extra cations at interstitial. Fine. And impurity defects, there is no further categories. Okay, so first we have to know what is point defect, and under point defect we have total 3 types. So point defect, from the name you can understand that there will be irregularities or deviation from the ideal arrangement around a point or an atom in a crystalline substance. So that is why it is called point defect. Now this point defect, it may arise because of different types of reasons. Now depending on these reasons there is different name that we will use. Now what are these reasons? The absence of a constituent particle. That means suppose one particle, it must reside at some particular lattice point but it is not present there, it is vacant, it is absent. That means there will be a defect. Okay, now second probability is presence of a foreign particle at the lattice point. Now when there is foreign particle present, that means it is also one type of impurity, because this particle should not be present ideally but it is present. So that is why it is foreign particle. So this is impurity. Presence of foreign particle at the interstitial site. The second one is at the lattice site. So what is interstitial site? So this is the space between lattice sites. So suppose here if I write, so here the interstitial sites will be this position. Okay, and the last reason is displacement of a particle to interstitial site. So here we do not have any foreign particle. The particle which should present at lattice point, suppose it is displaced to some interstitial site. So that is also another probability, and it may be the reason for defects in crystal. So point defects are classified into three types: stoichiometric defect, non-stoichiometric defect, and impurity defect. Now stoichiometric defect, from the name we have to understand that even after the presence of this type of defect, the stoichiometry of the compound will be maintained. That is why the name is stoichiometric defect. But if it is not maintained after the defect formation, then it will be non-stoichiometric. And impurity defect, it is simply because of the presence of some foreign particle. Okay. So what is stoichiometry defect? The compounds in which number of cations and also anions are exactly in the same ratio as presented by their chemical formula are called stoichiometric compound. So suppose we have any compound A2B3. So A is the cation, B is the anion, and after defect formation, here the ratio of A and B, it is still 2:3. So before defect formation also 2:3, after defect formation also 2:3. So that is why we are saying that stoichiometry is maintained even after defect formation. That is why it is known as stoichiometric compounds. And in this defect, there is no disturbance in the stoichiometry of the solid. Okay. Now there are four types: vacancy, interstitial, Schottky, and Frenkel defect. We will study each of these one by one. Vacancy defect. So vacancy defect, there must be some vacancy, right? So when some of the lattice sites are vacant, then we will say there is vacancy defect. So here in this position we have a vacancy. So here this atom should be present, but it is not present. So this result in decrease in density of the substance. So it must be so because density is mass by volume. So when some atom is missing, mass will be decreased and volume will remain same. That means here the numerator is decreased but denominator is fixed. So density will decrease. And this defect can also develop when a substance is heated. So when it is heated, that means we are providing thermal energy. So because of that energy, this particle may be removed. Okay, because to remove this particle, there must be some presence of energy. Okay, that is why that it may form when the substance is heated, but it is not mandatory that for vacancy defect we have to heat it. Okay. Interstitial defect. So what is interstitial, that we have already seen. In this picture, all these positions are actually interstitial position. Okay, so here you can see one particle is present at this position, but this is not its natural position where it should be present. It is not its natural position, but still it is present. That is why it is defect. So when some constituent particles occupy an interstitial site, we will say that interstitial defect is present. Now, unlike the previous one, that is vacancy defect, where density is decreased, now obviously density will increase. So this defect increases density of the substance because density is mass by volume. Volume is fixed, mass is increased. Fine. So that is why density will increase. That is the difference between vacancy and interstitial defect. And here we have to remember that under stoichiometry there are total 4 types: vacancy, interstitial, Schottky, Frenkel. But these first 2 types, that is vacancy type, first 2 type, that is vacancy type and interstitial defect, they are mostly shown by non-ionic solids. But if it is ionic type of solid, then mostly they show Schottky defect and Frenkel defect. Now why it is so? Because in case of ionic solids, electrical neutrality is of utmost importance. That means total positive charge and total negative charge must be equal. But if you consider vacancy defect and interstitial defect, in case of vacancy defect, suppose some cation is missing or anion is missing, so there will be excess positive charge or excess negative charge, so electrical neutrality is not maintained. Similarly, if you consider interstitial defect, some extra species is present, so depending on whether it is cation or anion, positive charge will increase or negative charge will increase. So electrical neutrality is not maintained in case of vacancy and interstitial defect. But electrical neutrality is very important for ionic solids. So that is why vacancy and interstitial defects are not observed in case of ionic solids. They are mostly observed in case of non-ionic solids. Okay, so this is very important difference between vacancy and interstitial on one side, Frenkel, Schottky on other side. Though all these four fall under stoichiometric defects. Now, what is Schottky defect? Mostly when we talk about defects, these Schottky and Frenkel, these two are very common. Okay. So in Schottky defect, obviously ionic crystal, because we have just seen that it is this type of defect is observed for ionic solid. So suppose the ionic crystal is A plus B minus. So here equal number of cations and equal number of anions will be missing from their actual position. So from the picture you can see here the green sphere, that is anion because it is larger in size, and the orange spheres, they are cation. So here anion is missing and here cation is missing. Okay, so that is when one positive charge is missing, one negative charge is also missing. That means electrical neutrality is maintained. This type of defect is shown by highly ionic compounds which have high coordination number and small difference in the size of cation and anion. Fine. So remember these two, based on these 2 points, we can observe either Schottky defect or Frenkel defect, because you will see in Frenkel defect the conditions are totally opposite. Fine. So if in any ionic solid the size of cation and anion are very close, though we know that anions are always larger than cations because there is more electron density, but if their size are very close to each other, that is small difference between their size, then there is a tendency to form Schottky defect. Okay, so for example, if you take all these solids, their here size of cation and anion are not varying largely, and coordination number is also very high, that is void space that will be less. Now because of this Schottky defect, there is some consequences. So what are these consequences of Schottky defect? Number of ions decreases as a result of this defect. Obviously one, because cation and anion both are missing, so obviously density will decrease, just we have seen in case of vacancy defect. Okay, because volume will remain same but mass will decrease. The crystal begins to conduct electricity to a small extent by ionic mechanism. Now it is because when cation and anions are missing, basically there is generation of holes. Fine. So it may be that one of the other anion will come to this place, so the new vacancy will be created or the new hole will be created here. Similarly, another sphere, if it is moving here, then the hole will be created here. So in this way the hole is changing its position. Okay, so when this type of changing in position of holes occurs, there is conduction of electricity. Okay, so that is why in case of Schottky defect we can expect small amount of electrical conductance. Presence of too many voids, because when there is missing of one cation, there is also one anion missing, so number of void is now very high. So as a result, what happens? Lattice energy decreases. Okay, and stability of the crystal, that is also decreases, because when lattice energy decreases, obviously stability also decreases. So these are the consequences of Schottky defect. Density decrease, it can conduct electricity, and the stability of the lattice is decreased. Next is Frenkel defect. Now in case of Frenkel defect, ion is missing from its current correct lattice site, that is the natural lattice site, so there will be a creation of hole, and what it does, it occupies an interstitial site. Now in case of Schottky, what we have seen, it is completely missing. It is not moving to some another position, but here it is moving to some another position. So this is the natural position of this cation, the orange sphere, but it is moving to some interstitial position. So this type of defect is known as Frenkel defect. So here obviously stoichiometry is maintained because it is simply changing its position, it is not missing, right? So stoichiometry is maintained, so that is why it is under stoichiometric defect. Now since cations are usually smaller, we know that compared to the size of anion, cation size is smaller, so that is why it is more common that they will be occupying the interstitial site, because interstitial sites are not very large in size, so it is easier for the cations to change their position compared to the anions. Okay, now this type of defect is present in ionic compounds when coordination number is low. So in case of Schottky, we have seen high coordination number, but here it is low coordination number, and larger difference in size of cation and anion. So this criteria is also completely opposite. Now there should be large difference in size of cation and anion. And the third point, highly polarizing cation and easily polarizable anion, if it is present, then also Frenkel defect will be common. So if you consider, see, all these are silver salt, right? And chloride, bromide, iodide, these ions, their polarizability is very good. So AgF is not present because F, its polarizability is not good. And Ag plus, which is from the cation is from D block. Okay, so its polarizing power is very high. Why? Because of the poor shielding effect of the D orbitals, what happens? Effective nuclear charge increases. So that is why charge density increases, so its polarizing power also increases. So Frenkel defect, they are observed in these types of solids. Okay, so what are the main point of difference between Schottky and Frenkel, we will see, but before that we have to know what are the consequences of Frenkel defect. Just we have seen in case of Schottky also. So for Frenkel defect, here no ions are actually missing from the crystal lattice as a whole, right? So what happens? Density, it will remain same, there will be no effect on density because the ion is simply changing its position, that's it. The closeness of like charges tends to increase the dielectric constant of the crystal. So here the cation, when it is moving to interstitial site, now same charge are close to each other, so this process, it will increase the dielectric constant of the crystal, and the crystal conducts electricity to a small extent by ionic mechanism, because here also when the cation is shifting its position, there will be generation of hole. So because of this vacancy or hole, as we have also observed for Schottky, there will be because of this generation of hole, another cation may come to this place, and if we look at the previous structure, here we can understand this fact better. So we have hole here, right? Now this cation, it may be moving to this side, now new hole will be created here, this cation can come here, new hole will be created here. So in this way the hole will change its position. So that is the reason for the electrical conductivity. Okay, next, difference between Schottky defect and Frenkel defect. So Schottky defect is formed when oppositely charged ions leave their lattice sites, creating vacancies. But in case of Frenkel defects, the smaller ions, which is usually the cation, that is displaced from its lattice position to some interstitial site. These vacancies formed in stoichiometric units to maintain overall neutrality, and in case of Frenkel defect, there is a vacancy created at its original site, and at interstitial defect at its new location. So when it is shifted to some new location, that is the interstitial site, so there will be excess cation or smaller ion. So in the new place there will be interstitial defect. Okay, so you can also call it interstitial defect, or it is also sometimes called dislocation defect. Okay, because the particle is dislocated from its original position. Density of the crystal will be decreased less than normal, but here it will not be changed. It occurs when there is small difference in size between cation and anion, and here it is opposite, large size difference. Okay. So it is to be noted that due to both of these defects, electrical conductivity crystal increases. That is, before defect formation and after defect formation, if you compare the electrical conductivity, it is increased. Now, as I have already said, that this is because of the holes created on account of these defects. So holes are created, then holes can change their position. So because of this change in position of the holes, there will be electrical conduction. Okay. So under stoichiometry defect, we have seen vacancy, interstitial, Schottky, Frenkel, 4 types. Now we will start non-stoichiometric defect. So in non-stoichiometric defect, obviously the stoichiometry will not be maintained. So if as a result of this imperfection, the ratio of number of cation to anions becomes different from that indicated by their ideal chemical formula, the defects are called non-stoichiometry. So suppose we have A2B3, A cation, B anion. So before defect formation, the ratio of A and B 2:3. But suppose after defect formation, the ratio is something else. Suppose it is 2:1. That means now the amount of B is less. So if the stoichiometry is disturbed, these defects we will call non-stoichiometry. Fine. These defects arise either due to excess of metal atoms. Okay, it may be because of the excess of metal atoms present. So when metal, suppose A is metal, B is non-metal. So if A is excess, so the stoichiometry will be disturbed. Now it may be that B is excess, then also stoichiometry disturbed, and there may be presence of impurity or foreign particles also. Now mainly it is because of 2 types, metal excess defect and metal deficiency defect. So metal excess defect, it is, we can easily understand that metal is excess, but when metal deficiency, that means this is also one type of anion increase, because when metal is deficient, that is positive charge is deficient, obviously negative charge will be higher amount. Okay. So metal excess defect because of anionic vacancies. Now under metal excess defect, there is actually 2 types. So we have here 2 types. The first one is anionic vacancy, that we will discuss now. So when metal excess defect occurs because of anionic vacancy, what actually happens? It has been observed. So here we will take an example, because by this example we can understand this in a better way. So suppose we have taken crystal of NaCl and we are heating this crystal of NaCl in sodium vapor. That means now the NaCl, it is in contact of some extra sodium atom. So now what will happen? A non-stoichiometric compound NaCl will be formed in which there is slight excess of sodium atoms. Now how it is happening, that we have to know. For that we will take the help of this picture. Suppose here A plus, this is sodium. Suppose A plus is sodium plus and B minus is Cl minus. So now it is in contact with some sodium vapor, that means extra sodium atom. What happens? Some sodium will be deposited at the surface, and when they are deposited, there is also that is removal of electron, so that they can be converted to Na plus. So there is generation of Na plus and also electron. So what will happen now? Some Cl minus, that is B minus in this case, some Cl minus, suppose this is one Cl minus, they will diffuse to the surface so that they can combine with Na plus. So now this Cl minus, when it is diffusing to surface area, this site will be vacant. Just as here you can see, this is the actual position of B minus or Cl minus, but this position is vacant. So now why it is vacant? Because it is diffused to surface area so that it can bind with Na plus and there will be formation of NaCl. Now this electron which is removed from this sodium, this will come here. So this electron is coming to the position of Cl minus basically. Okay, so this is the process. So here slight excess of sodium ions is there because we are treating it in heating it in presence of sodium vapor. So some sodium atoms are extra. So now the stoichiometry is disturbed. NaCl, the ratio of cation and anion is 1:1, but here it is not so. Here the ratio is 1 plus 1, 1 plus n is to 1. 1 plus n is to 1. Okay, so stoichiometry is disturbed. The anionic sites occupied by unpaired electrons are called F centers. So this is the F center. Now this F center, the name, it is actually from the German word Farbe. So in German language, Farbe means color. So as color is generated because of this electron, because as we are providing heat, the electron can jump from lower energy level to higher energy level, and if this energy gap falls under visible region, we can see some color. Okay, so when NaCl is heated with sodium vapor, there may be generation of color, and that is why as these electrons are responsible for this color, so that is why this center is also known as F center or color center. Similarly, in place of NaCl, if we take lithium chloride, because lithium chloride will also behave in a similar way because lithium is also from group 1 metal. So lithium chloride, when we heat it in presence of some lithium vapor, the color will be pink. And if it is KCl, that is we are heating KCl in presence of potassium vapor, the color will be magenta. Okay, so as color is generated, we will say that F center is created or color center is created, and the F, this term is coming from the German word Farbe, which means color. So this is metal excess defect because of anionic vacancy. Now metal excess defect can also be because of interstitial cation. So another type is because of interstitial cation. So what happens here? We will take the example of zinc oxide. Zinc oxide under normal condition is white in color, that is at room temperature. But if we heat it, what happens? The color is changed from white to yellow, and it loses some oxygen also. According to this equation, ZnO, we are heating it, Zn2 plus is generated, oxygen is removed, so now the amount of oxygen is less, and also there is generation of electron because Zn2 plus is formed. So now we can say that there is excess of Zn in the crystal because some amount of oxide ion, it is removed in the form of oxygen gas. So excess Zn in the crystal, and its formula will be Zn1 plus X and oxygen. So before defect formation, the ratio of Zn2 plus and O2 minus is 1:1, but now the ratio is 1 plus X:1. It is not same. Okay. These excess Zn2 plus ions, they can move to interstitial site, and the electrons are trapped in neighboring interstitial sites. So we have to look at this picture. Here A plus is suppose Zn2 plus and B minus is oxide ion. So A plus, that is excess Zn2 plus, now it is present at interstitial position. So these positions are interstitial positions. So Zn2 plus ion move to interstitial sites, and the electrons that are generated, electrons are trapped in neighboring interstitial sites. So this is also interstitial sites. So this electron that is present in neighboring interstitial sites. So cation is also present in interstitial site, electron is also present in interstitial site. This defect may be visualized as loss of non-metal atom. which leave their electrons behind. So as if here oxide ion is converted to oxygen. So that is why some electrons are excess. So these electrons are as if they are left behind. Oxide is already converted to oxygen gas and it is removed. It is not present no more in crystal. But the electrons of oxygen, it is still left in the crystal. So they leave their electrons behind. So this is the loss of non-metal atom because it is loss of oxygen. Okay. So because of these free electrons, which is basically generated from when the conversion of oxide to O2 takes place. Because Zn2 plus, it is already in cationic form. It is not that these two electrons are coming from Zn2 plus. These are actually electrons of oxide. Okay. So this may be due to these free electrons, electrical conductivity is increased. Okay. Because free electrons are present in the interstitial side. That is the reason. Because electrical conductivity, it may be because of free electrons and also because of holes. So because of holes, electrical conductivity, that we have already seen in case of Schottky and Frenkel, right? Now metal deficiency defect. Remember this slide, metal excess defect number 1 and metal deficiency defect. So now metal deficiency defect. Now metal deficiency means obviously cationic vacancy. So here A plus cation, B minus anion. Here A plus is missing. Cationic vacancy. So now stoichiometry will be disturbed, but the reason behind this is missing cation. There are many solids which are not very easy to prepare because in stoichiometric composition, because they always contain less amount of metal as compared to stoichiometric proportion. So metals are always present in lesser amount compared to the actual amount, that actual theoretical amount. Okay. So here when one A plus is missing, what happens? This extra, now negative charge is extra because one A plus is missing. So to balance this, another A plus is converted to A2 plus. In this case, one positive ion is missing from its lattice side. Extra negative charge is balanced by some nearby metal ion acquiring 2 charges instead of 1. Okay. So here our cation is carrying single positive charge. So when single positive charge is missing, another single positive charge must be converted to dipositive charge. Okay. Similarly, it may be another example if we show, that is for iron oxide. So in case of iron oxide, what happens? That is crystals of FeO. Here actually the ideal oxidation state is Fe2 plus and for oxygen it is 2 minus. Okay. So here these blue colored spheres, they are Fe2 plus. So when one Fe2 plus is missing, basically 2 positive charge is missing. So to balance this 2 positive charge, 2 extra positive charge must be created. So what happens when one Fe2 plus is missing from its ideal position? This is missing. Okay. Now another 2 Fe2 plus is converted to Fe3 plus. Because now we have 2 plus positive charge less, anionic charge is higher. So to balance this 2 negative extra charge, 2 Fe2 plus ion should be converted to 2 Fe3 plus ion, so that overall charge remains same. There is evidently a deficiency of the metal ions, although the crystal as a whole is neutral. So it must be because other cations are converted to Fe3 plus. So that is why overall neutrality will be maintained. This type of defect is generally found amongst the compounds of transition metals. Now why it is so? Because we know that transition metals can show different types of valency. You cannot expect it for sodium or potassium, because for sodium and potassium they have only one oxidation state, which is +1. It is fixed. But if it is transition metal, there may be different types of oxidation state. Just take the example of cobalt, cobalt 2+, cobalt 3+, iron 2+, iron 3+, copper +1, copper +2. That means here when one Fe2+ is missing, another Fe2+ must be converted to Fe3+. So if they can easily change their oxidation state, that means they have variable valency. So it will be helpful for this type of defect formation. So that is why this type of defect is mostly observed in case of transition metals. And here we have some examples. Crystals of iron oxide, iron sulfide, nickel oxide show this type of defect. So this is metal deficiency defect or cationic vacancy. Now impurity defect, because under point defect there are total 3: stoichiometric defect, non-stoichiometric defect and impurity defect. So in impurity defect there is no further category, so we will take just one example. So if molten NaCl containing little amount of SrCl2. So now see, until now we have only the original crystal, we do not have any foreign atom or foreign compound. But now we have molten NaCl which is in presence of little amount of strontium chloride. So this molten NaCl containing little amount of SrCl2, when it is crystallized, what happens? Some of the sites of Na+ ions now occupied by strontium 2+ ion. Now strontium, its positive charge is 2+, but sodium is only single plus. So what should be the case? Sr2+ must replace 2 sodium ions to maintain the same charge. So it occupies the site of one ion and the other site will remain vacant. So look at this picture. Here this is the actual position of Na+, but that position is now taken by Sr2+. Okay, and for 2 sodium plus ion missing, there will be 1 Sr2+, because sodium has single charge. So 2 positions of Na are missing, 1, 2, but one is vacant and another one there is presence of the foreign particle. So that is what is written here. It occupies the site of one ion and the other site remains vacant. This is the vacant site. These cationic vacancies thus produced, it will be equal in number to that of Sr2+. Obviously, here 1 Sr2+, for 1 Sr2+ there is 1 vacancy. Similarly, if you remove 2 more sodium, then suppose here we have Sr2+, so this will be vacant. So now 2 Sr2+ cation and 2 vacancy, 1 and 2. So that is why we are saying that the cationic vacancies thus produced are equal in number to that of Sr2+ ions. And another type of example that we can give is solid solution of CdCl2 and AgCl. So why we are saying solid solution? Normally when we say solution, what picture comes in our mind? There must be some solid and we are dissolving it in some liquid solvent, right? But solid solution is where both solute and as well as the solvent both are solid. So as if here you can see that NaCl is present in large amount and Sr2+, SrCl2, that is present in small amount. So one solid is inside another solid. So that is why we are calling it as solid solution. And another example is CdCl2 combined with silver chloride. Okay, so this is impurity defect. Now we will compare this. 1 minute. So here we have a problem. Match the defects given in column 1 with statements given in column 2 and mark the appropriate choice. So here in column 1, we have A, B, C, D, simple vacancy defect, simple interstitial defect, Frenkel defect and Schottky defect. So all are basically stoichiometric defect, because under stoichiometric defect we have vacancy defect, interstitial defect, Frenkel defect, Schottky defect. So all these four in column 1, that is A, B, C, D, all are under same category. And in column 2 we have shown by non-ionic solid and increases the density of the solid. So remember, non-ionic solid, they show vacancy defect and interstitial defect. Okay, and in which case density increases? It is in case of interstitial defect, because there is excess particle. So 1 should be matched with B, 1 with B. Then second one, shown by ionic solid, so it must be Schottky or Frenkel, any one. Decreases the density. So density decreases in case of Schottky. So D must be equal to 2. In the third statement, shown by non-ionic solid, so it means either vacancy or interstitial. By interstitial we have already used. So non-ionic solid decreases the density, it must be vacancy. So A is 3. And the last one is already left, so it must be Frenkel defect, shown by ionic solid, which is true, and density of the solid remains same. So in case of Frenkel defect, there is no vacancy created, only the position of the particle is shifted. So that is why density remains same. So C will be 4. So it is matching with which option? A 3, B 1, C 4 and D 2. So 3 1 4 2. So the last option will be correct. Okay. Another problem, this is assertion reason type of problem. So in assertion, the statement given is KCl more likely to show Schottky defect, while lithium iodide is more likely to show Frenkel defect. And in the reason statement is given, Schottky defect is more likely in ionic solids, in which cations and anions are of comparable size. And in case of Frenkel defect, it is more likely in ionic solids where cations and anions have large difference in their ionic sizes. So when there is large difference in their ionic sizes, we know Frenkel defect occurs. And when the sizes are very close to each other, Schottky defect observed. So reason is actually true. Reason is true. And assertion, that is KCl is more likely to show Schottky defect. So now compare the size of K plus with Cl minus, and also compare the size of lithium plus with iodide. So obviously lithium, it is from second period, and iodine, this is very larger in size. Okay, so that means there will be high difference in the size between lithium plus and iodide. So it must show Frenkel defect. So assertion is also correct, and K plus Cl minus, their sizes are close to each other. So this is also true. And in assertion and reason type of question, we normally have this 4 statement. Okay, so here assertion is true, reason is also true, and reason is the correct explanation of assertion also, because here for this statement the actual reason behind it, why KCl is showing Schottky defect, because its cation and anion sizes are almost same to each other. And why lithium iodide is showing Frenkel defect, because here large difference in size between cation and anion. So that reason is already mentioned here. So that is why reason is the correct explanation of A. So which option we should choose? It is the first option. Both A and R correct, and R is the correct explanation of A. Okay.